Hello everybody, I'm Sebastien Leduc in charge of software at Kalray. I'm going to talk about OpenCL as main programming model for the MPPA architecture. Let's start with a quick overview of Kalray. So Kalray is a public company with a global presence, and we are basically the leader in many core technology with our third generation MPPA processor. In terms of markets, we address both next generation embedded systems as well as next generation data center. So we do that either through standalone processors, but we also make our own PCIe cards with our processor on it to address dedicated or specific data center use cases. Let's now go to a quick overview of the MPPA architecture. So as I told you, the MPPA is a many-core architecture. So it features 80 core per dies in the third generation. So we can go up to 160 cores through the use of 2 dies into the same package. So it's system in package. It operates at frequencies from 600 megahertz up to 1.2 gigahertz. And it also features it's a clustered architecture, sorry. So each die has 5 clusters of 16 core each. So in case of system in package, we end up with 10 clusters for 160 cores. We also feature some high-speed interfaces. So we've got 16 lanes of PCIe Gen 4, and we have 2 100 gigabits per second Ethernet interfaces. Let's go to the compute cluster itself. So as I said, each cluster features 16 64-bit cores. It also has one additional core that is dedicated either to security or safety usage. It features 2 crypto accelerators to accelerate data center use cases, and it has a cluster DMA that can be used to transfer data from the DDR memory to the local memory of the cluster. So in terms of memory hierarchy, the L1 cache of the 16 cores are coherent within the cluster, but not between clusters. And we have 4 megabytes of local memory that can be configured either as local memory or as L2 cache with 3 different configurations. If we now go to the details of the processor itself, so the processor is the KVX architecture. So it's a proprietary architecture. It's a VLIW core with a 6-stage pipeline and 6-issue VLIW architecture. It features a MMU and instruction and data L1 cache, each of 16 kilobytes. And it has a very rich instruction set that features most floating point IEEE operators. So for 16-bit, 32-bit, and 64-bit floating point types. And each core comes with its coprocessor for machine learning and vision. So we call it TCA for tightly coupled accelerator. So it's a DMA-based architecture, which means even though all the cores can access the DDR, I mean the DDR, the full memory map is visible from each core, but to achieve high performances, it's better to transfer through DMA the data to local memory before processing it. Okay, I will now quickly introduce the Kalray acceleration framework. So Kalray acceleration framework is basically our software offering to ease the integration into middlewares. So it features 3 different programming models. So either you can do direct programming using either OpenCL, standard OpenCL, or OpenMP Dispatch from OpenCL. So I will come back to this in some later slide. we've got also domain-specific language, mostly for machine learning. So we have a machine learning compiler, which is called KNN, which allows to compile standard neural network described with standard frameworks like ONNX and TensorFlow, and compile it for the MPPA. And of course, we support API-based programming through libraries. So we support the most common libraries for computer vision, so OpenCV, and for mathematics, we have BLAS, LAPACK, and FFTW. So as you can see on this diagram, all programming models sit on top of OpenCL. So basically, they use OpenCL as offloading API. Let's now go to the details of how the OpenCL model is mapped on the MPPA architecture. You will see that it fits pretty well. So in OpenCL, the platform model describes a host, which is the processor on which the middleware runs, an OpenCL device, which is the device on which the host offloads some computing using OpenCL. The OpenCL device itself is made of one or more compute units. Compute units are made of one or more processing elements, and there is a notion also of subdevice, which is a subset of compute units of the parent device. So basically, you can partition a device into smaller device on a compute unit basis. And basically, the OpenCL supports two types of control flow. I mean, it supports both converged or diverged control flows. So if we now go to the MPPA architecture and see how this is mapped, so basically the host is usually an external processor, which will be a x86 or ARM-based architecture. The OpenCL device will be the MPPA itself, so the full MPPA. The compute units will be the clusters of the MPPA. The processing elements will be the cores of the MPPA, and it is possible to partition the MPPA into subdevice, which will be made of a subset of the clusters of the full MPPA. In the case of the MPPA, the control flow is diverged, meaning that each processor executes its own control flow, own program. So basically, they can really execute different programs. Now, if we go to the execution model of OpenCL, so as you know, there is a notion of work item, which is one instance of the kernel function. There is a notion of work group, which is a group of work items that execute on a single compute unit. And last, there is a notion of ND-range kernel, which is the index space for work item parallel executions. So basically, the grid on which the kernel will execute. So on the MPPA, basically the work item each work item will be executed by one MPPA core. The work group will be executed on one MPPA cluster, and then the ND-range kernel will be executed either on a device, meaning the full MPPA, or on a subdevice, meaning a subset of the clusters of the MPPA. If we go now to the OpenCL memory model, so the OpenCL memory model supports 4 memory regions, so global, constant, local, and private. So on the MPPA, basically, global and constant memory will map to the DDR of the MPPA. Local memory will map to the local memory of the cluster, so it's visible only in OpenCL by the work items that belong to the same work group. So this can be achieved on the MPPA. And then the private memory region, which is private to a work item, on the MPPA, it will be mapped to a per core private segment in cluster local memory. And to finish this mapping of the different OpenCL features on the MPPA, Let's go now to the OpenCL features. So as I said, the MPPA is a DMA-based architecture. So to expose the DMA transfers that are possible on the MPPA, we do that using the OpenCL async copy built-in functions. So either the default ones, I mean the ones that are part of the default specification, but we also support the lately introduced extensions, so CLKHR extended async copies. So these ones are for 2D and 3D async copies. CLKHR async workgroup copy fence. So this one is to give some ordering guarantees between async copy operations. And we have a few Kalray specific vendor extensions that we intend to push to the Chronos working group soon. So basically, the first one is async work item copy functions. So those ones are very similar to the async work group copy functions, but without the synchronizing behavior among work items of the same work group. So this can be quite practical in some use cases. And we have a bunch of new 2D and 3D extensions that make programming a bit simpler for the user. In terms of supported data types, basically the data types of OpenCL allow us to expose most of the MPPA data types. So basically 64-bit integers, 16-bit floats, 64-bit floats. So those ones here, I show them as extensions because we are conformant for the embedded profile. So those ones are optional for the embedded profile, but we do support them. We expose also all the MPPA extensive SIMD support through OpenCL vector types and math built-in functions. And the only type that we have that is non-standard, I mean that we cannot expose through a standard OpenCL type, is our tensor data type and associated built-in functions. So I know there are some initiatives to introduce some tensor data type in OpenCL, at least as an extension. So we are looking at that to see if we can, let's say, map to something more standard than our own extension. And the last point is MPPA atomic operations. So we support OpenCL 2.0 scoped atomic functions, which allow us to expose all the atomic operations that we support. So let's now compare the programming with OpenCL on a GPU versus on MPPA. So basically, if you look at a GPU in terms of architecture, GPUs usually have a SYMT architecture, which means that the execution of kernels is based on warps, which are group of threads that all execute the same instruction in a lockstep manner. So for this kind of architecture, the divergence cost is usually quite high. And also GPUs feature hardware hyperthreading and hardware scheduling of warps so as to hide the DDR latency. So on the MPPA, it's a bit different. Each processing element is a true core, which means each core can really execute its own program, so there is no divergence cost. It's a DMA-based architecture, which means that it's better to transfer data to local memory and process it in local memory instead of processing it in DDR. And of course, we have a lot more local cluster memory than on GPUs. This is just to allow that kind of programming. Now, if you look at the way a kernel will be written for GPU, usually it will have small work item functions that process one point of the index space, and the kernel function will usually access global variables, data in global memory directly. If you look at the MPPA now, basically, if you take a code, an OpenCL code that is written with GPU in mind, you just have to recompile it and it will be functional on the MPPA. So this is the beauty of using standards. But if you want to get high performance, you will have to follow some coding guidelines. So basically, it's better to have bigger work item functions that process several data points. This is because we don't have hardware scheduling of warps. So in our case, it's much better to have bigger work item functions. And it's also better to use async work group copy built-in functions to transfer data to the local memory before processing it. So this is not the case of most code you will find for GPUs. So in the case of MPPA, there is some rework of the kernels that is needed to get the best performance possible, but still staying with the within the OpenCL standard way of programming. Okay, I will now talk a little bit about OpenCL on the MPPA usage. So we passed conformance for OpenCL 1.2 embedded profile end of last year. We don't support image, which is an optional feature in OpenCL. We do support a bunch of extensions over the embedded profile. So we have support for 64-bit integers, 16-bit floats, 64-bit floats, all the async work group copy extensions. As I already said, we have a few Kalray specific extensions. So we have two buffer flags to control where OpenCL buffers are allocated. So the first one, it allows to create an OpenCL buffer in any of the cluster's local memory. So this is very nice to allow tunneling of two different kernels without going back to the DDR memory. And this is relevant on the MPPA because we have a lot of local memory. And the second buffer flag we have allows to allocate buffers in a memory region which is suitable for PCIe peer-to-peer. We have one extension that we call OpenMP Dispatch from OpenCL. So I will explain a little bit more what this programming model is on the next slide. And as I said just before, we have some more async copy extensions. So I won't go back to this. So quickly, an overview of the OpenMP Dispatch from OpenCL. So this is an idea that we stole from Texas Instruments. So they do that on their DSP. So basically, in this case, what we do is you use the OpenCL API to dispatch one instance of the kernel function on core 0 of each cluster. And then once inside the cluster, the dispatch within the cluster is handled using OpenMP. So basically, you just use some OpenMP pragmas to parallelize your code within the cluster. So this is pretty nice because then we still benefit from a standard API to deploy code on the MPPA. And some people prefer to use OpenMP or are more used to OpenMP. So in some cases, it's just for experimentations, but at least it offers some more possibility to the end users. So one point also that is quite interesting on the MPPA is the possibilities to partition the MPPA into several devices. So this can be done either at boot time. So at boot time, we can basically expose several accelerator devices from the same MPPA. So on this diagram, I've shown one accelerator that would be made of 3 clusters, and the second accelerator that would be made of 2 clusters. So both accelerators will appear as 2 different devices on host side, and then in that case, it's very easy to it's very easy to have different applications use different devices with strong isolation between the two devices. And the partitioning can also be done at runtime. So either through the use of sub-devices, or also we have a proprietary mechanism to do that. So that's quite interesting to run mixed criticality applications that have different constraints on the real-time characteristics or safety characteristics. Okay, now I will jump to the conclusion. So as I said, we reached OpenCL conformance end of 2020 on our third generation MPPA processor. For Kalray, I think the added value of using OpenCL is huge. Basically, it allows us to leverage the existing OpenCL code base. So there is a lot of OpenCL code that can be easily ported to the MPPA. There are also there is a kind of strong ecosystem around OpenCL with a lot of tools or libraries that use OpenCL as a offloading API. So I can just take a few examples like Cycle, TVM, or OpenCV that has an OpenCL backend. It also allows us to leverage existing OpenCL development tools. So again, I just mentioned a few like CodeXL or CLGrind, etc. Of course, it requires less effort from us on documentation. We just have to focus on the MPPA specific information, and we can rely on books and on the spec itself to document the programming model. And it makes MPPA adoption much easier because thanks to a standard programming model, our architecture seems, well, the adoption looks easier for people, which is good. And now if I look at from an end customer's point of view, again, it's not a proprietary, it's not a Kalray proprietary programming model. It's easier to find skilled OpenCL engineers. There is some flexibility for porting from one hardware architecture to another. And it also gives, let's say, better guarantees in terms of long-term maintenance and a much easier porting methodology. So I would say for us, OpenCL was the de facto choice as programming model for the MPPA. Thank you, guys. Have a good day. Bye.